Having computed some areas, our next step is to try to use our slicing approach to compute the volume or third-dimensional shape and see if the same approach will work. Let's take a look at this example here. We've got a triangular base on a pyramid, so this is like a four-sided die, and we can look at it in cross-section. When we get into 3 dimensions, we're going to spend a lot of time looking at sort of a 3D perspective view and also a straight-on view. And that'll be helpful for imagining how these slices work. So, if we would like to find the volume of this pyramid, it has a height of 5 units, and at the base, all the sides are 3 long. So if we looked at this side of it here, this would be 3. In other words, it's 3 along here, 3 along here, and 3 along here. The 5 would be the distance from the base to the peak. Now, how could we find the volume of this particular shape? Well, I think the most natural way is to imagine slicing it up into thin slices, like so, where each slice, we can imagine a number of different slices. It's a little harder to sketch in 3D now, but each of these slices would have a volume, and they would all be, we can call this whatever we like. We have to define some variables. I think we'll define it as h here. We'll imagine taking a step down from the top of the triangle, so a distance from here to here of h, and then the thickness of the slice would be a small change in that distance, so delta h. If that's the case, then what we need to do is find the total volume. The total volume will be the sum of all the slices we can make in this way. And so our challenge is to, having decided on how we're slicing, our challenge is now to find the volume, not area, volume of one slice. So the volume of one slice is going to equal, well, the nice thing about these slices is that they're just a triangle times a little thickness. So in that case, we know how to find the volume. It's the area of the triangle times the height. And the height, we already said, was a small thickness. It could be height. Sometimes it's easier to think of it as a thickness. And that thickness is delta h. Then, okay, so now we have part of the problem solved. We now need to figure out the area of a generic triangle, and we're going to get the volume by adding the third dimension, delta h. So our challenge is really to focus in on this area of a triangle. Well, what can we say about the triangle? Well, it's going to have a length, and let's call that L here. Whoops. Let's call that L in a new color. This distance here, and just like the base sides are all 3, this slice will have an equilateral triangle, all with length L, L, and L. And we have a nice formula that says, hey, if we have an equilateral triangle with all sides length A, oh, let's make our lives easier. Let's call them all A then. Then the area is going to be a squared with a coefficient. It's not actually a square, so it's not just a squared, but you can imagine some root 3's coming out because of the equilateral triangle ratios, side ratios. So if we can find out what A is, knowing what our distance down is, then we can find the area of this triangle. Well, actually, we know what it is. If we write it in terms of A anyway, it's root 3 over 4 A squared, and the height is delta h. And then we recognize that we have 2 different variables in here, A and delta h. We really need to have these A's written as h's instead to be able to do our integral at the next stage. So our challenge is not to say, well, I've got A, but I don't know what A is. We need to tie A and h together. And that's where the side view comes in handy. We'll have 2 triangles that are similar, one which is A to h, and one which is 5 to 3. And so we can use our similar triangles to say that A over h This to this is the same as 3 to 5, or A is equal to 3/5 h. And that, going back to our area of a triangle, lets us convert from areas or lengths of side A to the location of the slice. If I know where I'm making my slice, how far from the peak, then I can tell you what the length of the sides of that slice are. And so we get root 3 over 4. A is 3/5 h, and that's all squared times delta h. And we'll continue this on the next page. We'll simplify that a little bit. But the key thing is we found the volume of a slice. Notice it has 3 dimensions, thickness and 2 lengths, h here, and some coefficients. That's fine. So we're going to be able to convert that into an expression for the total volume by adding up all the slices. Let's see how that works. So the total volume is approximately the sum of the slices, and the slices we just said were root 3 over 4 times 3/5 h squared delta h. This was all our a here, and it was a squared. And so if we want to convert that to an exact volume, then we're going to need to replace the sum with an integral. Everything else stays the same. And the delta h is the only thing that changes. It becomes a dh as we imagine the slices becoming thinner and thinner. Then our last thing is to decide, where do our slices start? Well, we have all these thin slices all the way up to the top. And actually we measured h this way. So h was the distance from the peak. Well, the largest h we can get is the total height of the pyramid. So we'll have slices at height 0 all the way down to, or up to in value, h equals 5. And that is the most challenging part done, developing this integral in the first place. Once we have that, we can now evaluate. Okay, so having built the integral, we can now evaluate it. Some constants we've got, just be aware what we have to do here. We have the 3/5 squared. So I'm going to bring all the coefficients out front and then leave ourselves the simpler integral h squared dh. And what do we get from that? Well, we can expand a bit of this out. That's 9 root 3. That's 25 over 4. 25 times 4 is 100. And then we can focus on the integration. That'll be h cubed over 3, evaluated at 5 and 0. And so 9 root 3 over 100 times 5 cubed over 3 minus 0 cubed over 3. And that's 125. The 9 and the 3 can cancel, so we have 3 root 3, 125 over 100. And that's actually just 5/4. So we can have 15 root 3 over 4. And it's nice to put that in decimal if we can. We get 6.495 cubic units, or volume. Perfect. So that is how we'd actually evaluate the volume once we got our integral representing it. The challenge again is to get to this integral. The integration itself is fairly straightforward, if a little technical with the constants. For those who have seen the volume of a cone or other pyramid-like shape, you can also get 1/3 the base times the height, and the area of the base here is root 3 over 4 times 3. Anyway, you can go through the calculations. You'll get exactly this volume here as well if you use the standard formulas. But how we arrived at this is a more generic approach that we're going to generalize further when we continue on in this unit.